Now, integral calculus is actually older than derivative calculus, even though, as I mentioned before, a lot of it is undoing derivatives. But the invention of it, or the thought of it, actually came before derivatives. We talked in our derivatives units how Newton and Leibniz kind of are credited with coming up with calculus relatively at the same time, give or take 25 years. Just kind of funny to think of that as relatively the same time. But independently, integral calculus goes back all the way to the Greeks. And it was initially started with trying to figure out the area under a curve. Attributed to Archimedes, it's not great that it's called the method of exhaustion. You're like, oh great, this is going to be such a fun unit if it was referred to as a method of exhaustion. But the idea is if you had some sort of weird shape that you didn't know how to do the area of. So you don't have a formula. Like we have formulas for area of circle, we had formulas for areas of rectangles, they had formulas for polygons, but let's say you had some sort of weird shape and you were like, I need to find the area of this. First of all, do we know what this shape is called? No, because it has no name. Is there a formula for it? No. But Archimedes' method of exhaustion was, well, if I did those rectangles, the area would be close. But not very close. That was really like, but it would be an okay way to estimate it. However, if instead I did even smaller rectangles all the way, that area is actually closer. And I could make my rectangles smaller and get closer. And then I could make them smaller and get closer. And then I could make them smaller and get closer. Until I'm exhausted of making them smaller and getting closer. But I can get as close as I like as long as I'm willing to get as exhausted as I can. That was the idea. And it's really simplistic and brilliant. And it is sort of the basis of where integration started. But as they work backwards from integration, we now realize that it's just the undoing of derivatives. So we teach it after derivatives, because everything that is undoing is harder than doing. And it's always, you've done this ever since kindergarten in math. You do something, and that's like the first thing you learn in math, besides counting, is probably adding, right? After you've counted, right, everybody's introduced to math, like, what's 1 plus 1? And it's like 2. And then you add. And then you've added for a while, and we subtract. And I don't know if you remember, but subtracting was harder than adding. And then you learned multiplication, followed by undoing that, dividing. And even in our algebra, we learned multiplication, then undoing of multiplication in algebra, factoring. And factoring still is, to some students, is like, oh, because the undoing of multiplying is hard. So we always do something and then undo it, and the undoing is harder, and that's why integration, even though it was discovered much, much earlier than derivatives, and the connection was only made after derivatives were made, we learn it last. And we've been doing a bit of anti-differentiation already. Because on some of your units, I have like, hey, you want to work backwards? And then you were like, like, haha, I'm teaching you integration early, but it wasn't hard, and it just gets a little bit more complicated as we try to be more systematic. So, antidifferentiation is the reverse process of differentiation, so we call the antiderivative, or the integral, is the original function that would give you that derivative. So if you were told the derivative was 2x, I think you can do this one in your head. What would it have been originally? Well, it would have been x squared. And that, we also talked about this earlier, that, well, it could have been x squared just by itself, or it might have been x squared plus 5. And we're going to find out in this unit, we're going to always sort of go plus c, saying that, well, it could be any number there. It really doesn't matter. If I take the derivative and I have some constant, when I take that derivative backwards, it would be 5. Okay? Now, the interesting thing about just connecting this to the area thing that we have at the beginning, and just sort of giving you an idea of what's, wow, I cannot draw a straight line today. Let's make some dots. Here's 2x. One of the ideas of the area under the curve is going to look, oh, yeah, that's just, no, I'm not even going to grab it. Let's just put a smiley face. We'll leave that for later. It's all good. So this idea that there's an infinite amount, we have that plus c at the end, and sometimes we're going to be going in and solving for that plus c as we go. Notation-wise, if we have the derivative, then the original function is just going to be f of x plus c, and we call that the antiderivative. And we learn a new symbol to tell us to work backwards, which is the integral symbol like this. It's like a big long S, kind of like sort of what you see maybe in violin kind of thing. Kind of looks like that. So that's our integral sign, and that tells you, hey, this was the derivative. Can you work backwards to what it was originally? Right? The inside part we call the integrand. You don't need to know those things, just kind of interesting new words. Of course, whenever you have something somewhere, you have to give it a name. So, like, what do you call the thing inside of a square root? You have no idea, but there's a name for it, right? Just like this is the integrand, that's the radicand, or something like that. Maybe I'm making that. Seems like it's something similar to that. And sometimes you'll see in textbooks that if this was a little h, because it doesn't have the derivative sign, then when you work backwards, we'll call it a big H. So now what we have to do to create rules for working backwards, because right now, you just use intuition. Like when you saw the 2x, you were like, oh, I'll go to derivatives that I know. I could see an x squared, bringing that 2 out in front, no problem, right? And that's great, but as you get into more complicated numbers, sometimes intuition is hard, or your mental math is sort of like, oh, hurting my brain too much. So it's nice to develop a process. And the way that you develop a process is you first look at, well, what did I do when I did the derivative of the power rule? And this is just review, this wasn't hard. Oh, you're like, oh, you multiply the function by the exponent, you brought that 5 in front. And then you subtracted 1 from the exponent. So this was the process of doing the derivative. And now we have to undo. And the undoing process is not that hard. What would be the opposite of subtracting 1 from the exponent? We would add 1 to the exponent. What would be the opposite of multiplying by 5 in the front? Would be dividing by 5. Okay? So we had this question in our notes in our very second unit. Work backwards, right? And this one you just looked at and saw because it fit our power rule nicely, right? When we did this unit, you were like, oh, a number got brought on in front and you subtracted 1 from the exponent, so it was very easy to see that it was x plus x to the 5, right? In the first unit, I always said find a function, so this would be good, or x to the 5 plus 3 was fine. In our current unit, we're always going to write plus c to say there could have been anything. But now if we would use the process of working backwards process would say the last thing that we did was subtract 1 from the exponent, so the first thing that we should do is add 1 to the exponent. And actually we would just leave everything else the same and add 1 to the exponent. And then the second thing that we have to undo, because the first thing that we did was bring the 5 out in front and multiply it, we would have to divide by 5. And so the undoing process will be add 1 to the exponent and divide by the exponent. Whereas the doing process was when you take the derivative, you multiplied by the exponent and subtracted 1 from the exponent. Now this works out to the same thing. And had I shown you this in the derivatives unit, you would have been like, can I just do this? Because I can see it because it's so easy. But in our derivatives unit, we never had to work backwards with anything that was too complicated. Right? This one too, you could just see it. You would have said to yourself, all right, I had an x cubed. And then you said, if I did the derivative, the 3 would have come in front, and if I need to get a 12, that 3 would have made a 4 there. And that's how you would have done it in our first unit, and now we're going to have the plus c. If we think about the working backwards process, you would add 1 to the exponent and have to divide by the exponent, and you see that that would give you the same thing. Just a different way of thinking about it. In our first unit, you just looked at it and could see. What is going to be the advantage of having a method is for ones that when you look at, you just don't see very well. Like, if you had a work backwards, right? It's like, oh, not quite as nice to work with because there's fractions. And it's just enough mental math, right? We all have our mental math limits, where it's like, that's too much mental math, I'm shutting down. And that one looks like this one, you're like, yeah, 4 times 3, I got this. I'm okay. No. You had me at adding 1 to the exponent. That was, I don't even want to go to the 12/5. And then I don't want to think what I'd have to put in front. So when I multiply by 12/5, I would get 2/3. No. So this all of a sudden seems like it would be nice to have a method. So going backwards, the opposite of subtracting 1 to the exponent. Now you would add 1 to the exponent right away, and not even, like, you just rewrite the number in front. Not worry about that, because you can undo the multiplying part by dividing. So now we're going to add 1 to the exponent and divide, and then of course have to remember add a constant c. So this is the general idea of it, that you would add 1 to your exponent and divide by your new exponent. Of course, this doesn't work if your exponent is a -1, because then you'd be dividing by 0. But every other value would be fine, and in fact, it would be fine even if there was a number in front to begin with, that number would just stay. Just like in derivatives, a number in front doesn't affect how you do the derivative, it's just multiplying by some constant, that wouldn't make a difference either. Oh, there's the one with the number. So, what does this look like? You want to do the indefinite integral of 11x to the 5th in the integrals, so there's our integral sign, okay? And this part of the integral is telling you what variable you would like to do. So you remember implicit differentiation, we would take the derivative with respect to t, even though there was no t's in the equation. You could do something similar with integration. So you want to make sure you're saying, like, this is the variable that we're working backwards with. It's the x. So what we would get here is we would add 1 to our exponent and divide by our exponent. And this is where it's really nice, because that 11/6 isn't a nice number in front, right? If you were working backwards with this one using our old techniques, you'd probably be like, okay, I would have an x to the 6th, and then 6 times what is 11? And you'd be like, that's not in my times table. And you'd be stuck. And you'd probably be like, oh, it's cheating to write 11/6, because the 6 multiplied by that would go away and you get 11, but your brain would want to write 1.8, no, like, that's where your brain wants to go. It wants to go to an actual answer, doesn't want a fraction. But now we have a technique that just says, that's fine. Add 1 to the exponent, divide, leave our answer like that. Great, we can move on without overloading ourselves with mental math trauma. You know how in derivatives I said you would get really good at subtracting by 1? Now you're going to get really good at adding by 1. And sometimes, because you've been subtracting by 1 for so long, sometimes you're going to get them mixed up, and then that's going to cause all sorts of issues. So, we want to integrate this. Adding 1 to the exponent is going to be a -2, and then you'd have to divide by that exponent. Can you see yourself accidentally writing a -4? Maybe? No. Never make any mistakes with negatives. That's a you problem, Mr. JR. And some of the same strategies that we had for derivatives, and this one is a little typo, unless I fixed it in your notes. Does yours have a dx there? So just like in derivatives, we would want to first change this into a form that we could do. And here's another great example of where this new technique says add 1 to the exponent, divide by your exponent plus c, and now dividing by a fraction is the same as multiplying by the reciprocal. So if I multiply this by 2/3, I'd get 20/3 x to the 3/2 plus c. I think this is a great example of where the mental math part would probably not give you the 20 over 3 right away. Be like, I'm stuck. So this technique works really nice. All right, try this one on your own. A notation on this one is it has y dx, so you can't integrate a y with respect to x unless you then, first of all, change this, right? Y is equal to this, so I'll change that to x to the 3/7. This is what it's asking for. Add 1 to the exponent, divide by the exponent plus c. Because you're dividing by a fraction, you can multiply by the reciprocal, and you would get 7x to the 10 over 7, x to the 10/7 over 10 plus c. So now if you could do something in derivatives, and if you think what would it look like to work backwards, you can do it in integrals. So in derivatives, if we were adding and subtracting things, we could take the derivatives separate. So if we're integrating two things and we're adding and subtracting, we can integrate them each on their own separately. So now we just have to work backwards on each one of these parts. So the x to the 5, add 1 to the exponent and divide. The negative 3x to the 1, add 1 to the exponent and divide. And the 2 would just be 2x plus c. And I think in questions like this, you see the advantage of having that backwards process. Now you can do things very quickly. It's like, oh, I have a method. I just add 1 to the exponent and divide. Boom, I can answer all of these right away. Whereas if you were just figuring it out with mental math, you could still do it, but you might get slowed down every once in a while. And just like derivatives, right? If you wanted to do the derivative of this, well, we learned eventually there was a product rule. But often if you had a technique to simplify something, that would make your derivative easier. The same is true for, well, probably even more true for integration. If I multiply this out first, I get x squared plus 4x minus 21. And now I can integrate each of these separately. In questions, generally, you'd have to simplify complex fractions, like if you're dividing by a fraction. On those previous examples, I multiplied by the reciprocal. But if you have something like 4 over 2 and you leave it, I'm going to be fine with that. When you check your textbook answers, they will always have simplified everything. Now, we're going to have to work backwards on everything. So when you think about all of our derivative rules, we have derivative rules for power rule, product rule, quotient rule, chain rule. We had all those derivative rules, and then we had sine, cos, like new functions and exponential functions. We have all those rules for moving forward. If we're integrating, we want to eventually undo them. At this point, can't jump ahead too far. We've only learned one undoing. We're just undoing the power rule right now. So this isn't in a form that we can do. However, if you would factor this, you would notice that your x minus 2's would simplify. And so we could replace this, and this is just x minus 4 dx, which add 1 to the exponent and divide. Are you okay with working backwards from a constant just to be a minus 4x? That one is just sort of like knowing how to do the derivative. And then, of course, plus c. Now, another thing that we notice with derivatives having a number in front just stayed in front, didn't make a difference. Same thing with integrals, and therefore a property of integrals is that we can move, there's some constant multiplied by a function. We're allowed to bring that constant out, just do the integral on its own, and then go from there. Okay? And I do this next example for that reason, because the plan is for all of us to get this wrong. That's the plan. It's like, it's a great way of teaching, Mr. Jarrett. Set us up for failure. Thank you. So why? Because you'd be like, all right, I can do this one. I'm gonna integrate 20 over x. Just so you don't feel bad, I'll do it wrong for you. Okay? This is what I expect you to do. And you're like, no, I never make mistakes, Mr. Jarrett. All right, 20, add 1 to the, something went wrong. Because if I add 1 to the exponent, to the x to the 0, I get 0. And then if I'm supposed to divide by my exponent, I get 0, and I'm not allowed to divide by 0. So things have gone wrong, right? And that does mean that from here to here that's just absolutely wrong. There we go. Make myself feel good. Can't divide by 0. If we think back to that little note that we had, like it said, n can't equal -1. It works for everything but n equals -1. And so we look at this one, and at this moment, many of us would just say, okay, this one can't, you just can't do this one. But if we use this idea that if you're multiplying by a constant, you could bring it out in front. So I could choose to bring the 20 out in front, which would leave me with 1 over x inside. And the reason that's nice, and this doesn't always work, but the reason that's nice is there is hope that you see the 1 over x and say, oh yeah, I remember doing the derivative of something and getting 1 over x. That's the hope. The reality is that the way that our brains work, this is hard, right? When I tell you the answer, you might go, oh yeah. But at this moment, many of you are drawing a blank. Like, what derivative gave you 1 over x? That was a natural law. Some of you are still not like, oh yeah. Some of you are like, oh yeah, I forgot that completely. So here's an interesting thing about our brains. In the derivatives unit, you learned the derivative of the natural log of x was 1 over x. And you taught your brain to see natural log of x, and then that your brain triggered, oh, I can move to 1 over x. But our brain does an interesting thing that unless we really focused on that, working backwards when you see the 1 over x, you can't work backwards and see natural log of x unless you know that really, really well. I mean, we first see this in kids in multiplication and dividing. I can ask kids to multiply two numbers, and if they've got it memorized, they can say the answer. But sometimes if I say the answer and I say, what two things multiply to give you 63? They're done. They're like, I have no idea. Well, what's 7 times 9? 63. Oh, it's 7 times 9. But they can, only if you give the numbers can your brain go in one direction. But working backwards, sometimes your brain can't go in that direction. And sometimes it doesn't go in that direction because, for example, the 7 times 9, right? And there was a professor at the University of Manitoba that actually did a study on this. The kids that can't see 63 as 7 times 9 are sometimes because they learned the following. Oh, 7 times 9 is hard, 7 times 10 is easy. That's 70. That's one too many 7s. So then I'll go 70 minus 7, that's 63. The answer is 63. But when asked to go backwards, starting with 63, they'd be like, I should just randomly add 7 to that to get to 70, and then think of that as 7 times 10, but that's one too many 7s, so I should now get... So depending on how you learned how to work forwards, it might be harder to work backwards. And it was an interesting study in his part because he said, in elementary school, we actually like it if kids come up with different techniques to learn to multiply. It seems like it would be a good strategy for someone struggling in math to say, oh, 7 times 10 is easier, but that's one too many 7s, so I should subtract and get 63. And that kid gets the right answer, and there's no indication that they're going to have trouble in math later on because they're getting the right answer. But when you give them 63, if they don't have it on their memory or their ability that 9 times 7 was 63, now they can't work backwards. Now they can't factor in grade 10. Now they're getting frustrated in math. And a lot of these things we don't realize that when we learn something one way, we don't take the time to really think about that and say, okay, if I got that answer, could I work backwards? So we're going to see that in this unit, and that's what makes this harder, because if you don't have it, if you didn't remember or have it memorized that natural log was 1 over x, you're not going to recognize the 1 over x to work backwards to get the natural log. We want to find the integral of the derivative of 5x squared. So this d dx says take the derivative of something, and this integral says work backwards. So if we did this step by step, first of all it says take the derivative of 5x squared, which as a derivative, the 2 would come out in front, subtract 1 from the exponent, you would get 10x. And now it says work backwards. So if I was working backwards, I'd be like, oh, I should add 1 to the exponent and divide by 2 plus c. And you're like, oh, that's just 5x squared plus c. Does it make sense that you would get back to where you started from? Right? I'm going to give you an example of what we did, and make you feel really good about your mental math abilities. Okay? What I would like you to do is take 37 and multiply it by 89. Good. Now divide by 89. Good. What's the answer? Wow. Phenomenal mental math abilities. Right? Make you feel like, I struggle with that 37 times 89. Right? I'm impressed. And then that was a huge number, and then you took that huge number and divided it by 89. Got 37. Wow. Right? So the same thing is happening here, right? You're taking the derivative of this, but then the integral is canceling out, so you're sort of undoing what you did. It should make sense that you would get 5x squared, but since the integral is the last thing that you do, you would still need a plus c. If we did the integral first and then the derivative, okay, the integral would have, I'll do it the long way, and then we'll talk about the shortcut after, okay? Or maybe we should just get the shortcut over with. All right, we're done. Okay, now, the long way to do this question would be the integral of this would say add 1 to your exponent, divide by your exponent, plus c. That's the integral. Then the integral part would have the plus c. And then the derivative would say, all right, do the derivative of each of these things. In here, the -2 would come out in front, cancel out with that -2. Subtract 1 from the exponent. And then do the derivative of some constant. Well, that'll be just 0. And you do get back to what you start with. But in this case, there would be no plus c. So the shortcut is a lot easier, especially if I gave you something really hard inside, right, that you couldn't do the integral yet. Right, like, what's the integral of tan of sine of cosine x cubed? But then we could take the derivative of that and just like, oh, I just did all that hard stuff. Now I just undid it. And I'm back to where I started. All right, so this is our integration unit and a little introduction.